We are recording. Okay. Well, thank you everybody for joining us today. The main objective of today's presentation, the webinar, is to promote the NASA's 3D Printed Habitat Challenge. It's an information webinar, and what we want to do is give you enough information that it will inspire you to compete, be a part of this competition. And we're really glad to have you listen to us. And let me just make sure that, we'll get started. We have open phase 3 as of November 7th, and people are signing up as we speak. And NASA Centennial Challenges, the name comes from the Centennial of Flight. Centennial Challenges started back in 2003, 2005. That's when it was formulated. And what we desire to do is develop technology in a manner, or target technologies that could potentially change the world. And if you know, just a couple days ago, it was Wright Brothers Day, December 17th. And when they flew for 12 seconds, after 30 years, we had the DC-3. They're still running commercial flights. And then in another 30 years, we had the SR-71 Blackbird. And that is an amazing a plane that can fly faster than many times the speed of sound. And now we have the F-35, which has technologies that make it look like the size of a bumblebee on radar. And composite technologies. And so we want to develop technologies that can change the world and potentially make life quite a lot better. Right now, Centennial Challenges has 4 challenges that are going on right now. CubeQuest is small satellite technologies that could potentially provide infrastructure for space exploration. Vascular Tissue Challenge could actually produce, grow human organs or tissue that could help people who are sick, as well as do experiments in space without expending an astronaut. We have the Space Robotics Challenge, which delves into automation, and a lot of what we're doing in 3D Printed Habitat Challenge is in automation as well. So, with that, let me turn this over to Rob Mueller. He's one of our technologists here at NASA and working in the area of in-space construction. Rob, it's yours.
Hello, good afternoon. Can you hear me?
I can hear you.
Okay, thanks. The main technology that we're trying to address here is shelter. And the reason why we need shelter in space for humans is because it's a very extreme environment. And when I say extreme environment, we have to deal with a variety of different aspects of living in space. So first of all, it's a pure vacuum on the moon, and it's a soft vacuum on Mars. So we have to deal with vacuum when we're in space. Then next thing is thermal protection. There are large thermal swings between the equatorial regions and the polar regions, as well as the day and the night. So it can get very cold on Mars. It can get down to minus 80 C or below. And a warm summer day on Mars is about 20 C. That's about the best it will get at the equator. So it's a challenging thermal environment. We still have micrometeoroids coming in on the moon today. On Mars we have less because there's an atmosphere on Mars, a very light atmosphere, but micrometeoroids is certainly something we have to think about. And radiation protection is very important as well. To keep the human crew alive, we need some form of radiation protection from solar particle events and galactic cosmic rays. So that must be considered in the design. And finally, there's something that many people don't consider is when a rocket lands, the rocket engines have a lot of thrust. And so this creates a blast ejecta where particles are entrained in the high velocity gases from the rocket engine, and that can be as high as 2,000 meters per second velocity on the particles. So think of sandblasting at an extreme velocity. So these are all aspects that need to be considered, but it all boils down to one thing: shelter. We need shelter in space for the human crew to survive and thrive. Next chart, please. At NASA, we always try to quantify our goals and our results so that we can compare the results with the requirements and judge if a project has been successful or not. For a project that we've had in-house at NASA in collaboration with the U.S. Army Corps of Engineers, we generated this set of key performance parameters. We basically have 4 KPPs, key performance parameters. First one is the construction material. The state of the art today is using water-based concrete and polymer concretes and using a technology sometimes referred to as contour crafting, which is essentially 3D printing with a large robotic gantry 3D printer. That's what is available today. The threshold value is the minimum criteria for success that we use for these kind of projects. And so we'd like to be able to do the 3D printing using in situ regolith materials as the manufacturing feedstock, and we will accept imported binders. So you could bring a binder from Earth and to Mars and use that on Mars, and that would be acceptable, but barely acceptable. But really our project goal is to have in situ regolith materials, feedstock, and these concrete-like materials that we will use in space should have no imported feedstock material. So everything should be an indigenous material. And if you read the rules, which we'll get into later, they do point you in that direction. Second KPP is emplacement. Today we make subscale small gantry mechanisms that are fixed in location. These are commercially available, but they usually are very big and heavy, and they're in some kind of a warehouse or large hangar. And what we'd like is we'd like a full-scale gantry mechanism. So large scale means something that's maybe 30 feet or longer in length, and maybe 8 feet or wider in width, and maybe 8 feet or taller in height. So something of that scale, that is what we mean by full scale. Something big enough to 3D print a small house, about 500 square feet, and then or bigger. But really what our project goal is to have these full-scale robotic emplacement systems, but they have to be mobile because we want to deploy them in the field, deploy them in space. Our third KPP is construction scale. Today, in phase 2 of this challenge, we've been able to demonstrate successfully that a small concrete dome can be 3D printed 1.5 meter diameter. However, in the future, we'd like to make large-scale structures like landing pads or foundations, and our minimum criteria for success is a subscale optimized planetary structure, so in other words, a scale model of a real habitat. But our final project goal is to have a real full-scale habitat, about 1,000 square feet, for 4 crew to live in on the surface of Mars. Finally, our KPP number 4 is the printhead material deposition rate, and through various experiments inside NASA and at the Army Corps of Engineers, and also benchmarking with what's commercially available in industry, we've established these criteria. What you can buy today can do about 1,000 pounds per hour. What we'd like to see, and some experiments in-house have confirmed that this is very achievable, is 4,000 pounds per hour of a concrete-like material deposition rate. But ultimately, in order to make large structures quickly and efficiently, we need something like 10,000 pounds an hour of deposited material. Next slide, please. All right. At NASA, we've decided to divide additive construction into 2 large categories. First one is a 2D additive construction. This is a planar surface, something, think of a landing pad or a foundation or a parking lot or a dust-free zone or a thermal wadi, which is an area that accumulates heat in the daytime and rejects it at nighttime. So that's what we mean by 2D additive construction. Here's some pictures, examples of in-house work that we've done at NASA showing how these 2D structures could be achieved, but they have never been done using this technology. So we're asking you to come up with ways of achieving two-dimensional structures that are made using additive construction methods. Next slide, please. The second large category we call 3D additive construction elements. That implies a volume. And ultimately, this would be a pressure vessel, a pressurized habitat in the vacuum of another planetary surface, and it would provide shelter for the crew and for equipment, and even for maintenance of equipment. And so that's our ultimate goal, is to make large 3D structures on another planetary surface using 100% indigenous materials, and the robotics would have to be autonomous or supervised autonomy, because the time delay of the communications transmission between Earth and Mars, for example, is 20 minutes in each direction in the worst case, so you could have a 40-minute latency. That's far too much for teleoperation. So we really need technologies that are autonomous or semi-autonomous. Next slide, please. At NASA, we have a series of technology roadmaps which are publicly available. You can find these on the internet. And from Technology Area 4, this roadmap is called the Robotics, Telerobotics, and Autonomous Systems Roadmap. And it's a peer-reviewed roadmap. And we've identified the top technical challenge for robotics in general, but I think that they apply very much to this challenge as well. In that when you develop a robotic system that's mobile and has to have the precision to place material exactly where you want it in order to form a 3D structure or a 2D structure, it requires a certain level of technology. And here's a list, and I'm not going to go through each item in the interest of time, but these slides are available for your reference. And I'll just point to things like fusing vision, tactile, and force control for manipulation, and also this verification of autonomous systems. If you have a change, how do you verify that your autonomous system is still behaving how it should be behaving? Then another big item is this mobile manipulation that is safe for working with and near humans. Sometimes they call this co-robotics, where it's cooperative robotics, where humans are working next to robots. These are all things that need to be considered for future missions in space. So we'd really like you to think about the robotic technologies, and a big theme in this Centennial Challenge is automation of construction technologies. And I'll hand off to the next speaker, Mike Case.
All right, Mike, can you speak? Well, I can't hear you, Mike. I'll check.
Can you hear me now?
I can hear you now.
Good. Okay, thank you. That's a relief. It's to unmute the microphone. Good afternoon, everybody. My name is Mike Case. I'm a program manager at the U.S. Army Engineer Research and Development Center, Construction Engineering Research Laboratory. We have the lead for the U.S. Army in construction-related robotics. We are also partnering with NASA through an interagency agreement, and we have a cooperative R&D agreement with Caterpillar as well. So about 3.5 years ago, we started a new program called the Automated Construction of Expeditionary Structures. And the vision for this program is to be able to print custom-designed expeditionary structures on demand in the field using locally available materials. It's printed at the top of the slide. So the bottom line here is whenever we have to do a contingency operation or maybe some disaster relief or things like that, we need to send people forward, often in situations that are dirty, dull, and dangerous, sometimes not so dull. And carrying all these people and logistics forward is dangerous, and it imposes quite a burden on the operation. So the point of this program was to see how much automation we can do, and ultimately our vision is to totally automate the on-site construction process in theater. On the screen, you can see our early concept from 3 years ago of a gantry-style construction system. And across the bottom of the screen, you see over the course of 3 years the progression that we went through from building some prototype gantry systems, printing some walls using cementitious material, working with Kennedy Space Center and Marshall Space Flight Center. The third slide on the bottom, third picture, is some testing we did of beams that were actually printed, and they performed quite well. You see some culverts. The Marine Corps asked us to produce some custom designed culverts to replace ones that they had to destroy. And then you see an early jersey barrier, which is just a look at making obstacles and things that could be used in the field. Next slide, please. So Rob mentioned key performance parameters, and we worked on the ones he talked about. In addition, what we really wanted to do was try to decrease the number of people. And in this first run, we were trying to get from a typical squad that would construct a plywood, what we call a B hut, is a barracks hut, from a squad of 7 or 8 people down to 2 to 3. Ultimately, we'd like 0, but this was the first step. We'd like to get the time down from 4 to 5 days to less than a day. We want to decrease the amount of materials that are shipped into theater. Currently, we have to ship plywood and various types of wood products from all over the world. And we also want better quality structures. Next slide, please.
I want to request, it looks like the guests are able to try to share their screen. If you could stop that, that's messing things up. You shouldn't be allowed to do that, but anyways, please stop.
Okay.
Go ahead, Mike.
Okay, thanks, Tony. What you see on the screen, hopefully, is an example of the first ever and largest printed structure in the United States that was printed in place using concrete with large-scale aggregate. We used speed systems that we worked with NASA to develop. We used equipment that we worked with Caterpillar on. And we were able to print this wall, or this building, the walls, in about 21 hours of print time. So that's a good first experiment. And we've shown a proof of concept that this can be done. Now the challenge, I would say, is where do we go from here? And what I'd like to point out, and the inspiration for the challenge here, the shelter challenge, is working at scale. And what we found is working on a small laboratory scale is a far different matter than working at a scale the size of this bee hut, which is 16 feet wide by 32 feet long by 8 feet high. Next slide, please. So what we in the Army are hoping to get from you who participate in the challenge is progress on a number of gaps that we see. First and foremost, in the area of autonomy. What we found with concrete, I know some of you may use different types of polymers or so on, is that there's still a lot of work involved in mixing and cleaning, that we're going to have to figure out new approaches to achieve autonomy where we have 0 people on site. Another step, in some of the BIM challengers could do this, is to get a digital thread that goes all the way from the BIM software, in other words, a design of your choice that can go all the way to printing with whatever type of printer that you have. Materials are still a challenge, and especially handling materials at scale. So being able to extrude material through a nozzle and print is one thing, but being able to handle on the order of multiple thousands of pounds of material over the course of a few hours is a whole nother challenge. So don't ignore the challenge of mixing the materials and getting it to the nozzle. A couple other things, I won't hit everything. Reinforcement is really a challenge. I would be happy to talk with anybody about some of the structural work we've been doing. If we're going to have people occupy these structures, then in fact, you need to look at things like vertical and horizontal reinforcement, shear strength of walls, things like that. And then finally, we want to look at about the print quality. So what did you actually end up printing, and does it meet the specs to be a secure, life-supporting, and life-safe facility? And that's it for me. I'll go ahead and pass it on to the next speaker.
All right, thank you, Mike. And if we communicate with competitors, we'll have to do another webinar to make sure everybody has an opportunity to hear what you say. I will turn it over to Mike Richnick from Caterpillar. And by the way, this challenge is being conducted by Bradley University. They are the challenge administrators. Unfortunately, when school's out, they kind of disperse to the winds. And Mike, as the Caterpillar representative and sponsor, is covering for them.
Thank you, Tony. I think if you could go one more slide forward, I still see the gap slide from Mike's presentation. Thank you very much. So I will be giving you just a big picture flyover of the challenge, and some of the speakers following me will come back in and fill in a lot of the details. As you've heard already from Rob and Mike about the significance of this challenge, these are just some comments made by John Vickers, who's a principal technologist at the Space Technology Mission Directorate. And clearly, participating in this challenge is moving the technology forward that will be required for us to have a sustainable presence of people on other planetary bodies. And as you can surmise from companies like Caterpillar being involved and the Army Corps of Engineers, we're also very interested in how these technologies can improve life here on Earth as well. Next slide, Tony. All right, so there have been 3 phases. We're currently in phase 3 of this 3D printed habitat challenge. The first phase really focused on architectural design and had $50,000 available for prizes. The second phase we just completed in August of this year with the head-to-head competition, and that was requiring the teams to develop a material for printing and print and evaluate structural members such as the compression test cylinders and flexural test beams, as well as the dome that Rob Mueller described as at the finale at the head-to-head. And so we had additional prize money, a $1.3 million prize purse available for that. And phase 3 is the most challenging that we've had yet, and that will culminate with printing a 1/3 scale habitat. And so we have, NASA has made available $2 million for the prize purse that is available to be won. You can go to the next slide, Tony. All right, so again, just at the highest level, and Mike Case mentioned this, we really want this to run from the design through the construction phase. So as a result, the teams are going to be challenged to design a habitat using BIM, Building Information Modeling software, to create a architectural design for a habitat meeting the required specifications, 1,000 square feet or 93 square meters, which can be printed using an autonomous or semi-autonomous 3D printing system. And so it all begins with that architectural design and concept, and will culminate with building, as I said, that habitat at a 1/3 scale at the end of April, beginning of May 2019. This is a large challenge and runs for a long period of time, so we have 5 checkpoints along the way, which I'll show you a little bit more on the next slide how those lay out in terms of timing. But we have 2 submissions for virtual construction and 3 submissions for actual printed construction. And it's really important to note that there are really 2 ways that teams or individuals can compete in this competition. The full registration and full competition requires that the teams participate at all 5 checkpoints. So the 2 virtual construction design checkpoints as well as the 3 physical construction checkpoints. But we also offer a reduced registration fee for people who would like to participate solely in the virtual construction levels. That opens the competition up to people who might not have the time or resources to actually develop an autonomous 3D printing system, and allows them to bring their creativity forward and design a habitat using BIM tools. You can go to the next slide. This is the timeline, and it shows, just for reference, the architectural phase 1 and the structural member phase 2, which again have wrapped up. Phase 3 registration is open and closes on February 15th. And then what you can see is we really have a 60% design checkpoint that comes middle of May. And then the first physical construction, which I'll give you a little more information on, that'll be due July 11th. And we space out then the following physical milestones at about 5 months apart. So the next submission of physical construction will be in December. And again, the final physical construction will be at the end of April in 2019, and we'll have the final virtual construction or design submission January 16th of 2019 before that final construction is completed. So we've tried to space the competition out to give teams enough time to meet these challenges. You can go to the next slide, Tony. All right, so as I mentioned, there are 2 checkpoints for virtual construction, and you'll hear more about those in detail coming up. But again, there's $200,000 available for that, $100,000 for each level. Again, the first level will be at a 60% complete design, and you can see the levels of design are specified for the various systems and the structure and pressure retaining walls and components. So initially, the first deliverable will be to complete a virtual construction submission of the design, and then the next phase will move into physical construction for those participating in physical construction. And then again, we'll come back around and require a 100% complete design as shown here on the slide that will be submitted in January of 2019. You can go to the next slide. All right, so as far as the construction levels or physical construction levels are concerned, there's a total of $1.8 million available for those 3 levels. There are $400,000 available at level 1, $600,000 at level 2, and $800,000 to be split among the top 3 teams potentially at level 3. And again, this is really trying to move the teams through different levels of complexity. So the first thing they do will be, among other tests and other evaluations they'll have to do again, which you'll hear more about later. But they'll start with printing a foundation, so that's sort of that 2-dimensional construction that Rob Mueller mentioned. And then from there, we'll be looking to determine if the teams can print something leak tight. So we'll have a hydrostatic testing phase where the teams will print what's loosely being called a bucket of water, so we can make sure the teams have that capability. And again, the final event will be a head-to-head competition to build that 1,000 square foot habitat at a 1/3 scale. You can go on to the next slide.
Just to note that at the head-to-head competition, the Caterpillar guys really put out the red carpet for everybody.
Yeah, thank you. We had a really great time here in August with the teams that were able to be here with us in Illinois. So I'll just close out my section here talking about the challenge structure and sponsors. Again, obviously this is a NASA Centennial Challenge, and as Tony Kim mentioned, Bradley University is the allied partner to execute the challenge. And the teams, you'll actually note when you register and sign your team agreements, those are all between the teams or individuals and Bradley University. So Bradley is in charge of administration. Caterpillar Incorporated, who I represent, is the main sponsor, the industrial sponsor, to help execute the competition. And we do that in partnership with many entities, and a couple of them are listed here on the chart. We heard from Mike Case from the Army Corps of Engineers earlier, and NASA and the Army Corps have a memo of understanding to work on these types of technologies. And then Caterpillar has been fortunate enough to be able to engage several sub-sponsors, one of which is Bechtel Corporation, which is one of the largest global engineering, construction, and project management companies, and the American Concrete Institute, one of the leading authorities and resources worldwide for concrete design, construction, and materials. And then also, we're proud to be sponsored by Brick and Mortar Ventures, and Curtis Rogers is on the phone. I'd like to give him a second to talk about their interest in the challenge.
You're muted. Curtis, you're muted.
Yep, thank you, Tony. And thank you, Mike. So my name is Curtis Rogers. I'm Principal Vice President at Brick and Mortar Ventures. Brick and Mortar Ventures is a seed stage venture capital firm in San Francisco that was founded by Darren Bechtel about 2 years ago. And our mission is to disrupt the way that we design, construct, and maintain the built world. And our contribution to this competition is really the perspective of the innovators. So the entrepreneurs, many of them are competing in this competition. Not only are they trying to push the technology and compete and go after the prize money, but they're also serving clients here and now And we also represent some of the early adopters in the construction space, so the most innovative construction companies and innovative clients. But as a member of the rules team of the competition, that's part of my contribution, is making sure the rules incentivize participation by entrepreneurs.
Thank you very much, Curtis. Excellent. So again, that's really the flyover, and I moved quickly, but I really wanted to make sure the time was available for the real experts to talk in more detail about the virtual construction and physical construction levels. So I'm going to pass it over to Dr. Palin Gutzigan-Weiser of Via Technic, and she is going to talk to you about the BIM and the virtual construction levels.
Hello everyone. At this phase of the competition, we are looking for the virtual database of the to-be 3D constructed design building, and this design model can be developed by using any BIM software that provides interoperable data export. So BIM as a building information model is an object-oriented parametric model developed in a collaborative process that includes the digital representation of physical and the functional characteristics of the building systems. And the deliverables of these levels are going to be including the functional metadata of the 3D printed habitat components, 3D printing construction process, and that will be useful for the whole life cycle of the structure. So as you might see in the slide, there are a couple of BIM uses that we are mostly interested in. 3D BIM habitat modeling, and this will include the metadata integrated model and design review process used to depict an accurate representation of physical conditions, printing environment, and assets of the facility. And next BIM uses construction sequencing, which is going to be graphically representing the both permanent and temporary facilities on site during multiple phases of the construction process. And another BIM use is the equipment flow. It's going to be depicting the 3D printers and all other autonomous systems movements on site while printing the material. And the last for the BIM model that we're interested is the virtual mockup, which is aimed to design and analyze the construction of the 3D printed building component to improve the planning and the constructability of the specific systems. And as in the next slide, you will see the minimum program requirements. And this 3D printed habitat design will consist of 1,000 square feet of livable space with 46 square feet environmental control and life support systems. The design will be also coordinated with the structural and mechanical, electrical, and plumbing system layouts, and at least exterior wall penetration will be included. And the space layout will be designed to be functional space planning for 4 astronauts for 1 year. So when we go into details of the virtual construction level 1, which is in the next slide, design development, 60% design complete level. So in this level, what we are looking for is the habitat modeling that I just described. And this is going to be developed in the detail of 60% design complete. And this will have MEP and ECLSS design systems, which is environmental control and life support systems. And these are going to be at the level of, at the LOD 100. And structural and other architectural systems are going to be at the LOD 300, which is the level of development defined by the BIM forum, which is a generally accepted specification that you can find the whole specifications at bimforum.org/LOD. And the model review sessions will be evaluated during the judging panels, and those are going to be evaluated by the completeness of the model, BIM use functionality, and aesthetic representation. And for these, submissions must be provided to Bradley University by May 16th. And at the end of the evaluations, 5 teams with the highest scores awarded by the amount of up to $100,000. And as in the next slide, in addition to the first level of construction, virtual construction level, what we are also looking for is optional 4D BIM models related to construction sequencing, equipment flow, and the virtual mockup that will be customized to 3D printing construction process. And the level of detail that we are looking for is at this time is 100% design complete. And in terms of modeling, MEP and environmental control and life support systems will be at LOD 400. And of course, the evaluation will be extended to the realism of the 4D modeling review as well, and the submissions will be submitted to Bradley by January 16, 2019. And at this level, 3 teams with the highest scores will be awarded up to $100,000. And in the next slide, you'll be seeing how the BIM deliverables is scored. And this is going to be done by the judging panels. And the submittals submitted by the competitors will be at interoperable data format. And the judges will be evaluating these models in a free viewing environment. And what we're also asking competitors to submit is, for the preliminary review, is an MP4 format, a review of the BIM model, and a scale 3D print of the structure. And as subject experts explained, automation from BIM to 3D print is highly encouraged. And in detail, you see the evaluation of the metrics. One is the completeness of the 3D model through LODs for 3D evaluation, which is comprising to 25% of the scoring system. These are going to be evaluated by the elements of LOD and the detail of system information. And the second scoring criteria is BIM use functionality, which is comprising the 50% of the scoring that will be evaluated by layout programming, layout efficiency, and 3D printing scalability. And the third criteria is going to be aesthetic representation, comprising the 25% of the whole score, and the fourth, which is going to be an optional point, going to be evaluated and scored by the realism of 4D models, which is 20%. So these are the virtual construction levels that I can summarize.
Thank you, Palin. Okay, now we are going to the actual, the construction levels. And to describe those, Tracy Prater of NASA Marshall Space Flight Center will present that information. Tracy, it's all yours.
Sure, thank you. So 3D printing, we refer to that also as additive manufacturing. Within the context of this competition, we define it as the process of depositing material layer by layer from a digital part file. So this is already being demonstrated at somewhat of a large scale for construction, as we saw through the Phase 2 competition. So the advantages of this technique for construction is that it removes some of your design constraints. It does reduce material waste. You can put material only where it's needed, and reduces the time from art to part. So it's also accelerating materials development. We also saw that in the Phase 2 competition. And so, you know, we'll be looking with this competition to just further advance those technologies and also focus on use of in-situ materials as well. Next slide. Next slide.
I've advanced it.
Oh, okay, thanks. There's, I see it now. Okay, So NASA and other space agencies really recognize the potential of this class of technologies for space exploration. When you go to a planetary surface, there's not going to be crew there. These are intended to be precursor missions where you would have autonomous construction systems that would fabricate structures, particularly from local indigenous materials, to build up infrastructure prior to the arrival of crew. Also able to reduce our launch mass if we are able to capitalize on those in-situ resources, and that's part of the focus of this competition. And then there are also applications for disaster response and military field operations. Next slide.
I guess it takes a little bit of time.
Yeah, that's okay. I can start talking it. So the vision of the Centennial Challenge competition is to really advance automated manufacturing and materials technology. So phase 3, as Rob and others have talked about, is very focused on autonomy, but we're still trying to incentivize you to use indigenous materials and mission recyclables, which would otherwise be trash on a space mission. So another element to this are sustainable housing challenges as the world experiences aggressive population growth in the next 100 years, and then also infrastructure repair and construction also tends to be very labor intensive in its current state. So looking at automating those processes and by virtue of that making them safer. Okay, so we should be on slide 4 now.
Right.
Okay.
Competition materials.
Okay. So I can't see those slides, but okay. So phase 3 of the Centennial Challenge, we're focused on materials, again, creation of construction materials and polymer recyclables. So if you're familiar with the phase 2 competition, we're using a sliding material scale, once again, to rate material selection based on relevance to planetary missions. One important difference or point to note from phase 2 is that you won't be penalized anymore for the use of imported materials. So imported materials are materials such as water, which would be transported from Earth specifically for construction purposes. There's also no minimum indigenous material requirement. However, as you'll see when we look at the sliding scale of materials, indigenous materials are scored more favorably. So for polymers, the sliding scale is based on the frequency of the use of those materials in packaging for space station. The rock-based aggregate scale is based on relevance of those materials to a planetary surface, specifically Mars. So moving on to slide 5.
I've changed it. It's a competition for materials. It's still phase 3 materials.
Okay, slide 5 is the acronym sheet.
Yes.
Okay, good. I can't see the slides. So slide 5 is the acronym cheat sheet for the materials that you'll see on the sliding scale. So it's polymers and aggregate materials. And then slide 6 shows the sliding scale. So again, there are several classes of materials, rock-based, polymers, additives, and bonders. And within each class, materials are assigned a rating factor based on their relevance to planetary missions. So your material score is obtained by taking the 3DP factor assigned to each material and the amount of that material by weight present in the formulation, multiplying those and summing them all together.
Next chart.
So slide 7. So other notes on material scoring, you will need to provide video and document evidence of the material selection and the mixing process, and that's needed really for the judging panel to be able to validate your mix and award the appropriate score to you. And again, if you have a material that's not represented on that sliding scale, we do just ask that you submit an inquiry to the judging panel and they will assign something specific to your particular material. And so for phase 3, within each construction level, there are 3 construction levels. 100 points of 1,100 will be allocated to material selection. So there's somewhat less of a focus on materials and what particular materials you select than there was in phase 2, but it's still an important element of the competition. We're still trying to incentivize you to use indigenous materials and trash recyclables, which is part of the vision of this competition. Okay, So slide 8, we'll start walking through the construction levels. So construction level 1 is somewhat of a 2D construction portion of the competition. We're asking you to print a foundation that's 2 meters by 3 meters by 100 millimeters thick. And so that will be evaluated for both smoothness and levelness per ACI 117, which is an American Concrete Institute standard that governs tolerances for concrete construction. The other aspect of the level 1 is a material durability test. So you'll be doing the freeze-thaw test that takes about 2 weeks. And for that test, as well as the compression test, you'll have to use a certified test lab to do that evaluation. The slab durability test is to subject the foundation to an impact by dropping an item from a specific height, a 5-meter drop. And so that would be done by the teams at their facility. And then for material strength, we would be looking at a compression test with a cylindrical specimen and then the maximum load that your material could withstand. So slide 9 goes more into level 2. So that is focused on printing a habitat element, so a walled structure with an optional roof, and then subjecting it to a hydrostatic leak test. So filling the structure to 2 different levels and then documenting the rate of drop in the water level to measure leakage over a certain period of time. And there are also some penetrations for this part of the competition that can be designed by the teams, and then also assessing the accuracy of the placement of those elements. So one important note here is that if you're competing and you don't substantially change your material between level 1 and level 2 or between level 2 and level 3, you don't have to resubmit the results of specifically the freeze-thaw test or the compression test. Okay. So slide 10 should go through level 3 and the head-to-head competition. So you would be, we'll be inviting 8 teams to the head-to-head, a maximum of 8, and you have to build a 3rd scale habitat on site. And so the test that would be performed on site would be a smoke test to measure leakage from your structure, impact testing via a drop test, and then crush testing to look at kind of the ultimate strength of your material. And so that's it. So again, lots more detail on the construction levels of the competition, specific material test, and how materials are scored can be found in the rules document. But if you do have questions about those as you enter into the competition, we ask that you submit those questions and we will publish those in the form of an FAQ. So thank you, guys.
Thank you, Tracy. As a wrap-up, I want to re-emphasize again that go and look at the rules on the Bradley website, and you can see the website right there. It's www.bradley.edu/challenge. And also, hopefully you've submitted some good questions that we might take an opportunity to answer here. We've got 10 minutes. So, Janet, I'll turn it over to you if you could give us some questions.
Sure thing. Can you guys hear me?
I can hear you.
Okay. We have several questions, so I'll start with the first one. The question is, are prefabricated pressure-retaining membranes, such as non-load-bearing inflatables, to be used in tandem with load-bearing printed walls prohibited?
That is a really good question, and we're going to have to get that one in a FAQ, I think, to give it a worthy answer.
Okay, no problem. And just for everyone on the line, we are recording all of the questions that are coming in via email, so if we don't get to them on this call, we'll certainly answer them for you afterward. Okay, next question.
Oh, by the way,
go ahead.
Just to give you a flavor, the sealing aspect of the autonomous sealing aspect of the structure, the spirit of the competition is that we wouldn't have a membrane, but we will discuss this amongst the team and get you an answer.
Okay, great. Here is the next question. For virtual construction, can you compete in both levels 1 and 2 or just one of them?
Mike, why don't you go ahead and take that one?
Yeah, I think if I understand the question correctly, if you register for the virtual construction portion of the competition, you would be eligible to compete in both levels 1 and 2 of virtual construction.
Okay, thank you. Next question. This one's a little more specific to the rules. In Appendix 3, for material 3D printed factors, can additional polymers be added, or are we only limited to those listed?
Tracy, why don't you take that one?
Sure. So we can certainly add material, and we did this for phase 2, right? We added materials on a case-by-case basis. Again, if you're using something that's not reflected in that sliding scale of materials, as by no means a comprehensive list of materials you can use, particularly for phase 3, you can use absolutely anything. We would just evaluate that on a case-by-case basis. And again, trying to keep to the spirit of a competition and think about its relevance to planetary missions or to recycling material that would otherwise be nuisance material.
Great, thank you. Next question. In contrast to the construction level rules, no mention is made in the virtual construction levels of defining the material mix. Is this not a requirement in the virtual level?
So,
That's it. Tracy, I can't hear you.
Sorry, so this is a question for Palin as well, since she's working the BIM side, but the BIM models do have to have some information about how you would actually construct, your design, but I don't think we're evaluating the material formulation in those levels as we are with the physical construction levels.
yeah, especially at the 100 design detail, we usually decide on the material, and the material composition needed to be integrated into virtual model.
And I guess in the final level, the final construction level, all of this kind of comes together where you actually have to show that the BIM model translating into the 3D printing aspect of it, and ultimately material testing. All of those come together in the end.
Mm-hmm.
Okay, great, thank you. Next question. For virtual construction, is the registration fee for level 1 and level 2 included into one fee?
Yes. Yeah, it's just one fee. You can compete in both levels of the virtual construction.
Great, thank you. Okay, next question. In Appendix 3 for material, I'm sorry, I already asked that one. Okay, this one's a bit longer, so bear with me. I might have to email this one to you guys. Section 8.2.12 states that any modifications of the structure after 3D printing is complete will result in a score penalty. So the question is, does this mean that teams are not being asked to have to lay out an architectural design outside of printed elements?
You were breaking up there, Janet.
Oh, sorry. How is it now?
It's a little better.
Okay, I tell you what, Tony, I'm going to email you this question too, so you can read along.
Okay.
This one's a bit long, just so you can see it as well. Okay. Section 8.2.12 of the rules state that any modification of the structure after 3D printing is complete will result in a penalty. So the question is, does this mean that teams are not being asked to consider habitat layout and architectural design outside of printed elements? Are teams being asked to ignore how a hab could be outfitted post-printing with interior elements like soft goods, etc., or how prefabricated structures could form part of the habitat?
Yeah, I think. Oh, go ahead, Tony.
Go ahead.
No, I think, just as a general comment, for the physical construction, we realize that the physical construction is really to demonstrate the structural and pressure retaining elements of the habitat. it's not going to have, you know, soft goods and those types of things. The mechanical, electrical systems and so on will just be simulated, but you'll note some pass-throughs for conduits and so on. So really it's focused on those elements in the physical construction. Now, I turn it over to Palin. In the judging of a virtual construction submission, however, you know, additional detail, you know, showing additional insight into interior finishes or things like that, I think that could be considered favorably by the judging panel, even though it would not be part of the physical construction competition. Is that a correct statement, Palin?
Yes. And we are going to be looking for the details with the specified LODs, which is also defined at the specifications of the beam forum LOD.
Okay, thank you. And we've got one final question here from a gentleman who is on right now, who's listening, and I just wanted to, I'll put this to you guys. They are manufacturers of an ultrasonic test system that can monitor the strength development of fresh material, including, but not limited to, things like concrete, from mixing to final strength. And they were wondering what the best way is to reach out to potential teams and at least let them know that they're, what they've got is available. So what's the best way to let teams know that their product is, you know, something that might help them in the challenge, or maybe partner with them?
Yeah, I think, you know, Janet, if you can just get that contact information over to me. One thing that we are working to do is basically just to have a non-confidential presence on the internet where teams and individuals can meet and greet and share non-confidential information and perhaps, you know, formulate teams. And so that might be an appropriate place to list some of these parties that are also interested in helping the teams out.
Thank you, because I'm sure we'll have more of those. And I did just get one last question that just popped in. Is Appendix 3 for material 3DP factors, and Appendix 3 can, oh no, actually, no, this looks like the same question, I think. Can additional aggregate or elements be added, or are we limited to those listed? I think this is the same question just coming in again. You guys addressed that.
Yes. Hey, Janet, I do want to say that that Facebook group that we hope will develop, people will have to be invited, so they need to be part of the interested parties, and the only way you can do that is to indicate to Bradley University through the website that they are interested. So they need to go in and act as if they are going to register or ask for registration information, and Ann McMullen will get in touch with them.
Yeah, that's a good point, Tony. Thank you.
That's all the questions so far.
Oh, okay, great. And I want to just say that people are still welcome to send in questions to that web or email address, and we'll try to address it. I think you all had some really good questions, and really appreciate the interest that you've shown. Maybe next time we might even make this interactive. Appreciate all the speakers and the effort that you put in to present this information, and I hope it has been really useful for you. And please come and join us for this competition, and we can change the world. And so with that, it's been an hour. Thank you so much for all the interest, and we'll be signing off. Thank you very much.
Thank you.
Thank you.
Thank you.
Thanks.